Okay, so before we move into image formation, with lenses, we want to work through a few of these conceptual questions. And so our first question, upon entering a medium in which the speed of light is 1.5 times 10 to the 8th, from a medium in which the speed of light is 2.0 times 10 to the 8th, what will an oblique ray do? And oblique here means at some angle with respect to the normal, so it's not coming vertically down. Will it be bent away from the normal, bent toward the normal, travel along the normal, travel perpendicular, or remain undeviated? So here we have a speed, it's entering a medium in which the speed is slower than the medium from which it is incident. So with that in mind, we have a higher speed in the incident medium than we do in the refracted medium. So what's going to happen here? So going back to above, right, we have some of these pictures, and if I have this condition, right, if I have this condition where light is coming from a less dense to a more dense medium, then the ray will get bent toward the normal. Okay, so that is the answer to the first question. So it should get bent toward. Okay. Number 2, in air, a source of light has a wavelength of 590 nanometers. What will the same source be underwater? So remember, water is a more dense medium than air, and so in a more dense medium the frequency stays the same, but the speed slows down. So if the speed slows down, then the wavelength also therefore has to shorten. So it should be a shorter wavelength. Okay? Number 3, we have a critical angle is that of incidence for which the angle of refraction equals, and this is the angle at which the light ray will move parallel across the boundary, which is 90 degrees to the horizontal. So the answer here should be 90 degrees. Okay. And number 4, name an important communication system component that makes use of total internal reflection. And here the answer that we just discussed at the end of the last video would be optical fibers. All right, and again, they're highly valued for transmitting data. All right, so now we want to talk about lenses and image formation with lenses. And the basic idea with lenses and image formation, all right, is if I have, and this is why glass is used when we make things like quote-unquote glasses. Glass, we can control the design of very easily. It's very cheap to make, and we know the index of refractions of the different types of glasses that are the most common. And so what we can do is exploit those properties of refraction for those specific types of glasses. Now, some are using things like acrylic and whatnot, but we can easily manipulate these materials, right? And so the idea is that suppose I have a piece of glass and part of it is a perfectly smooth part of a sphere. So this curvature would represent part of a sphere that if I, kind of went around, it would make a total sphere like this, right? And I have some light rays coming in and hitting the sphere, okay, the spherical portion of the glass. If this truly is part of a sphere, then it's going to be symmetric. And what that means is there's a line right through the middle that we call the optical axis that cuts the spherical portion in half, top to bottom. And if incoming light rays are parallel with that optical axis, okay, if incoming light rays are parallel with that optical axis, then what happens is all of the light rays will get bent toward a specific point. So these higher rays that are coming in are going to get bent a little bit more extremely than the rays that are closer to the optical axis that experience less bending. And so the result is they all get bent such that the rays meet at very close to the same point, and that once again is called the focal point. Now, this would be for a converging lens, okay? The convex side would be a converging lens. And if I have a diverging lens, okay, then this would be where the hemispherical bowl or the concave portion is where the light beams are hitting. And so suppose I have some light rays that are parallel with the optical axis, and they're coming in and they hit the boundary. These beams are going to diverge and get bent away from the optical axis. But they're all going to get bent in such a way that it would appear that if I trace these beams backward, right, if I trace the refracted beams backward, it would appear that they all originate from the focal point of the lens, okay? So in the diverging lens case, the rays appear like they are coming from a specific point when they're really not, but it looks like it, okay? So different curvatures from different lenses means different focal lengths, okay? So if I have a more slightly curved lens than a more noticeably curved lens, right? This is a more sharply curved lens. Then the more gently curved lens is going to have a much longer focal length. And the reason being is because this spherical portion represents a much larger sphere. If the curvature is very slight, that's a much larger sphere than this lens would represent, okay? So the shape of the lens does affect the focal point. Now, for people who manufacture eyeglasses, this is very important, right? Because this is the whole point of correcting vision problems. No one size fits all, because different people have different levels of, say, astigmatisms, and so not all defective eyesights are the same. So you need to be able to grind your lenses with different focal lengths. So they're all going to have slightly different shapes. And that allows, now in the case of eyeglasses, the differences are going to be extremely small, right? The curvatures are going to be extremely small. They're the curvature differences, I guess I should say, are going to be extremely small, but with large consequences, because if anybody has put on a pair of glasses that was not their prescription, then you know that things can look really, really blurry and fuzzy. And so the only way to fix that is to have precisely the correct size lens, right? Now the same kind of diagram holds for diverging lenses, right? For diverging lenses, the light comes in, and instead of being bent through the glass and then back toward the focal point on the other side, these rays will diverge, but it will appear like they came from the focal point on the side of the incoming rays, okay? And most optical systems, many optical systems, are a combination of both converging and diverging lenses, and they find wide use in instruments like cameras, telescopes, microscopes. All of these usually have a complex system of lenses. The main exception to that would be the very simple telescope where I have just two lenses, and those two lenses, if I make a very simple telescope, are usually going to be converging lenses, both of them, and one large lens to collect the light and bend it in the middle of the tube. Not in the, well, the focal point won't be in the middle, but it'll be in between the two lenses. And then the other lens is used to focus that light that has passed the focal point of the first lens toward your eye, okay? So for simple image construction, here's what we do, okay? So suppose we have a lens, and we draw an optical axis right through the middle of the lens, and that cuts the lens in half. And so then we assume, okay, we have an object, okay, and we're initially going to look at the converging case, right? We're going to look at the converging case. And I say, okay, if I have this object here, and let's say I know the focal length, and by the way, for a simple converging lens, I have two focal lengths because it doesn't matter which side of the lens I use. A simple converging lens has the same curvature on both sides, and so this is a symmetric lens. So what that means is both sides have focal points that are equidistant from the lens. All right, so that's going to be important. And so I have my object. I've got my two focal lengths, or two focal points. We call these the focal points, and then the distance from the middle of the lens to that point we call the focal length. Okay, so the position of the focal point, you can think of the position of the focal point as the distance from the lens to the focal point, and that is the focal length. Okay, but I do want to be precise with my terminology here. So we have our object, and this object is a light emitting object or light reflecting object. It doesn't matter. Okay, it can be a candle that's emitting its own light, or it can be a person who is reflecting the ambient light. But in any case, okay, what's going to happen is some of the light is going to travel toward the lens, and some of the light is going to take particular paths. Now, it's not just that these particular beams are the beams that make up the image, but these are the three easiest beams that we can use to find the image. And these three special beams are as follows. Number one, I can assume that there's going to be a beam that is going to be parallel to the optical axis being emitted from the object. And when that beam hits the lens, it's going to be refracted inside the lens, and then it's going to be refracted again when it hits the air, and it gets bent, and that beam will go through the focal length. Okay, that beam will go through the focal length. So an initially parallel beam to the optical axis will get bent and move through the focal length, okay, or the focal point. Okay, it'll move through the focal point. A second beam can be emitted from my object, and if that beam has the particular path where it moves through the center of the optical axis, so it hits the center of the lens where it crosses the optical axis, it goes right through the lens, and it is unrefracted. Okay, this particular beam does not get bent, and it just continues straight through. A third beam moves through the focal point on the object side. It moves through the focal point on the object side, and if that beam then successfully hits the lens, it will emerge parallel. So here's the symmetry. Initially parallel, then it moves through the focal point. If it initially moves through the focal point, it emerges parallel. And for a simple lens, these three beams, and in fact all other beams will do this, all other beams that hit the lens will also meet right here. It's just that these are the three easiest beams to analyze mathematically. And so all of the beams that are emitted from the object that pass through the lens will converge at this point where my image is. So here's where we call the image, okay? And we often denote the distance between the object and the lens as this distance S. The distance from the lens to the image is often denoted as P, and the distance from the lens to the focal point is the focal length F. Okay, so in the next video we will look at some rules for how those three variables are related, and look at an example of how to calculate one if the other two are known. And by that I mean if I know what my initial distance between the object and the lens is, if I know my object distance and I know the focal length, can I predict where the image is going to be? Also, this image will in fact be upside down. So if I hold a converging lens out beyond the focal point, things in that lens will appear upside down to my eye. Okay, If I bring them up very close, it will actually then be magnified and upright. And that's the idea behind the magnifying glass. All right, we'll